Start. It's a real pleasure to introduce Giulio D'Agostini, who we're keeping in the kind of Italian theme, and although we'll change that right at the end. So what I'm going to do is I'm going to read out the title because I'm quite intrigued by the certain ambiguity in it. So, basic probabilistic in the sciences and in forensics. Hopefully,
I think I was spoiled.
Oh, no, you're on. Oh, that's okay. Hopefully clarified by a toy experiment modeled by Bayesian Network. So, are you on?
No, it
Oh,
was.
right, good, yeah. So maybe you can explain whether the hopefully applies to forensics.
No, the
or to clarify.
hopefully is to clarify, because
okay.
I'm pretty sure that someone will be confused then. But also in this case, if you're confused, it's a good sign. Then you can start thinking again. If you reshuffle your ideas, sometimes it's good. What is bad is always to keep all the ideas and go on. But I assume that for most of you, this argument is quite familiar. So I have here some initial quotes just to say about what is probability for me. Probability is just probability. It was a Latin word which was used as probability until somebody decided it was something else. Okay, probability is good sense reduced to calculus. Now I'm very pleased to be here. I thanks very much to the organizers, and as many of you, I think I will shortly introduce myself, because here there is such a variety of people coming from different fields. So in this case, I'm an experimental particle physicist, okay, but I use this one, but not a former physicist doing forensic physics science. I just continue to do physics. I think for these months I came here to learn, and if I can, to perhaps help a little bit. I don't know if I succeed. Okay. And I'm here because I'm interested in probability, and in fact in the particle physics community I'm somehow known as a Bayesian expert. There is a program of mine which is used everywhere. I think essentially they know me, but I have to clarify that I'm not a Bayesian, as I'm not a Fermian, I'm not an Einsteinian, and so on, in the sense that physicists do not like this kind of labels. Okay, this is very important. Then, the second thing, I did not learn Bayesian reasoning on books and courses, but I reinvented myself when I started teaching. Okay, it was fun. After 3 months, I got many of the results of Laplace, even more, and only later I found that they were already famous. Indeed, I had done a calculation. I was disappointed, but I was happy, because being close to Laplace is not bad. In fact, in one of the calculations, I did a mistake. Laplace didn't. Okay. Anyhow, so you find more in my web page. As a physicist, I start from measurements straight. So we do measurements every day: electricity, blood pressure, radioactivity. This is a bit different. Higgs, perhaps you heard years ago Higgs in the media. Higgs going into gamma. It was a few years ago. These are two photons invariant mass. It is the mass of the two photons. Invariant mass of the photons around 125 GeV. 1 GeV is one proton essentially as mass. Okay, so it's 125 heavier than a proton. This is the detector we use for this kind of measurement. Not myself. I'm not in this collaboration. My friends, which are of this size here. It's just to understand which kind of monster we are talking about. Many tons, millions of electric channels, okay? And there are people who understand the little part of everything. We like to understand things. Okay, and this, for example, it's a measurement, so it's a gamma. These are two flashes of lights with a lot of background in a very noisy environment. And for example, this could be Higgs in gamma, could be. Probably not. Okay, probably not, because we have high background. In fact, at the most, this kind of events could have a few % chance of being really Higgs particle. Nevertheless, we estimate the mass value, the production rate, with uncertainties. As we see, it's a quite indirect measurement of something we do not see. We do not see the Higgs. We see tracks, but we don't see tracks. We invent tracks. What we see are the hits, okay, the electronic channels which just they have a spike, and then we reconstruct again, then we invent tracks, and then the calorimeter and so on. So it's a very complicated measurement. Now the question is, do we see masses? The people, when they tap, do we see voltages? Okay, sometimes we can feel voltages, but we do not see voltages. Do we see blood pressure? We can feel, oh, I'm weak, but we do not see blood pressure. Certainly not. Although for some quantities we can have a vivid impression. Impression I use in the David Hume sense. For example, if I try to raise an object, I feel the gravitational mass. If I try to push at a constant acceleration, I feel the inertial mass, but obviously we do not see. We have to rely somehow in instrument, but we have a feeling of what we are talking about. So mass, length, and so on. And as I'll tell you, also probability, we have somehow in our brain a kind of feeling. Otherwise, we couldn't understand it. And in fact, why we don't understand the quantum mechanics? Because our brain is not prepared to understand it. We can make all the computations, all the calculations, nobody understands, it works, fantastic. But anyhow, I will not talk about quantum mechanics. So when we make a measurement of a mass, essentially in this case we use a physical law, which is a set of equilibrium. There is a force which goes down, then there is the action of the spring up, okay, and then there is somehow a reading, okay. And this depends on the gravitational acceleration, the constant of the spring, and then what we do from the scale reading, which is the number we read, we have to guess our mass. Now, as you can understand, that there is a lot of complications. Why? Because, for example, G. What is G? G is very easy, you find in textbooks. It's just a gravitational constant, the mass of the Earth, and the square of the distance from the center of the Earth. But in reality, it's much more complicated, because the position is not at a nominal value of the distance from the center of Earth. The Earth is not spherical, it's not even ellipsoidal, it's not even homogeneous. The shape of the Earth is tautological. It's a geoid. The shape of the Earth is the shape of the Earth. Okay, a sphere and ellipsoid are good approximations. Then we have to take into account the centrifugal effects. We are turning around. Okay, then the effect of the moon. And obviously, this doesn't matter if we want to check our weight, if we have taken half a kilo. But when we do science, everything can be very important. We have to think about. And the same, this depends on K, temperature, no linearity, and then how this compression is turned into an angle and on the scale reading, and where the oscillation stop damping and so on, and all the variability of the quantities of influence. I like to mention here the ISO standard. This is a guide of uncertainty measurement, reading scale and so on. Okay, what is M? You see, as soon as we start to refine what we want to measure, it will be very difficult. Okay, and remember, it was mentioned by Paolo before, something like that. Pure empirical information, this is not a measurement. A number outside a constant, without all the contextual information, provides a little knowledge. It's not a knowledge at all, it's just a number. Mistrust the dogma of the immaculate observation. The pure observation doesn't make science. It's all the frame which makes that. And in particular, our conclusions on the credibility of the hypothesis of interest might depend on the question asked. Now I cannot go through the details, but yeah, I can play the Monty-Hall problem with variations, or the prisoner the three-reason problem, which is absolutely analogous. And you see, depending on the question which was asked, from the same answer, we can get different possibilities. Okay, and remember, performing an experiment is just a subclass of questioning. We are questioning nature somehow. Okay, and this can be very relevant in forensic. In the previous talk, I heard, the last of this morning, he could comment on the report. He couldn't say his opinion, which is very crucial. Okay, because depending on what you are allowed or not allowed to say, the things can change. Okay. Now, learning from data, what do? We have observation, we have hypothesis. Sometimes we have a discrete set of hypotheses, sometimes we have a continuity of hypotheses, like the length of this table. And this is to remember that the quantity, this is to remember that the quantity has a meaning only inside the model. You change the model, the quantities change completely. Okay, so essentially we go from observation to hypothesis, which is something you know. And also, when you do forensics, you go from observation of different kinds to hypothesis. Okay, so we go from past to future. Now, I'm biased with the physics, so you will read often physical word, but essentially the process of learning is more or less the same. So our task as scientists is to describe the physical world and to make inference on the laws and the parameters and predict observations. Okay. We have uncertainty. Why we have uncertainty? Because given the past observation, we are not sure about the theory or the parameter, okay, the values of the parameter. Even if we were sure about the theory and the parameters, there could be some internal random effects, like in quantum mechanics, or we are uncertain about the initial condition, the boundary conditions, and we are uncertain anyhow, even if we understand, we know everything, okay? And then we have to make decisions. So in the case of a physicist, what is the best experiment you want to do next? In the case of normal decision of people, what to do, okay? And I insist, I had some comments in the first workshop at the beginning of September. We shouldn't forget that decisions of judges are not only probabilistic. I think as far as I understand, I try to read a little bit in these months, okay? There is always a mixture of probability, how much you believe something, then there is how much is dangerous. So it's a decision. If this is very risky, you as a judge are more careful. Then there is even an educational issue. And we know in the history people have been killed for nothing, only to give you the examples. Now you say, oh, now our judges do not do any longer. I don't believe so. Okay, but anyhow, deep reason of uncertainty, why we are uncertain, essentially we are uncertain about the causal connection, cause effects. I'm using here the language of causes, as you can imagine in physics, very convenient that we are used to, but obviously, as it was discussed this morning, in reality is conditioning very generally. But in physics it works so often. But we have to be careful. Causation can be very risky. Okay, I already mentioned David Hume. I will mention him again. Okay, so the causation is always, but we have to use. There are people which have never read Hume, they only they've read the criticism, and they say, oh no, it's bad because he denies the causes. If you read Hume, he says, they are just risky, but we have to act, and then we build up our models. He was a very reasonable man. He was called by the French guys, Le Bon David, the good David. It was very fantastic, because he had understood the human understanding. That's nice, and then I think he was superior to many things. Very frustrated for the fact that the people did not read his books, but anyhow, it was okay. Let's go on. So, what means causes and effects? Now that you understood, don't misunderstand me, please. So, we have different causes which produce different effects. So, now, if we are in a special condition, from one effect you can go back to the causes. It's very simple. Everything is deterministic, but it's not like that. Okay, for example, you observe E2. Where does it come from? We are not sure. And then we have to go back. And now these are the problems which are the essential problem of the sciences. This is a guy you will see later. He makes this example. I play cards with a person. I can ask what is the probability to pick up a king, to turn up a king. And for this deck of cards was 1/8. And this is a problem in the probability of effects. But now I play with somebody I do not know, okay? He has got the king many times. What is the probability that he's cheating? This is a problem in the probability of causes. It may be said it is the essential problem of the experimental method, okay? And now it's a matter of fact, we, at least my generation, but also students now at university, they are not taught in this way. They make they use a very strange statistical method for the thing, but not how to go to the probability of the causes. Okay, And then when we make a measurement from a true value, I call mu the true value, x is the observation. So if we know if we assume a true value, then we are uncertain about x. If we are even uncertain about mu, we are more uncertain about the experimental response. But if we know the reading of the data anyhow, the observed data is certain, is the true value to be uncertain. In all books I was reading, we were teaching us about data uncertainty. I think it makes no sense. What means uncertainty? Are the data corrupted? If they are corrupted, the data are the corrupted data. Okay. What is we are uncertain is about the true value from which this value comes from. Okay. We are uncertain about mu given x. And not a symmetry reasoning, and I can guarantee you, when I discuss with my colleagues and friends, this reasoning is very natural, even if we are learning statistics in a very funny way. This was the reasoning of Laplace, of Gauss. When Gauss was deriving the Gaussian distribution, he was still writing Latin 1809, and he was speaking about the probability of the true values, okay, and then the probability of effect. And then he assumed that the true values were equally likely, okay? And then he was inverting and so on. It was absolutely the normal language. Okay, now let's make an experiment. Since I'm an experimentalist, I told you, make an experiment very easy here now. So mu can only assume 6 possibilities. X is binary, 0, 1, it will be black and white. Later, not now, but it's possible to make mu continuous and go on. So this is, I carry the experiment. So, moment. I have different experiments. So in this case, the experiment is this one, so I don't get one. Sorry, I had to prepare before. This is not okay, they are so mixed that to save time, I will do it. These are 6 boxes. In reality, for transportation purposes, the boxes are just bags, this kind of bags. I pick one really at random. I think I should go around and so on, but I think this goes fast. Now, this bag has 5 balls, black and white. Okay, we don't know which one, so they can be all black, all white, and all the intermediate possibilities. There are 6 in total. I just picked up one. To show you what I'm talking about, I take this one, which has a special label. Here I know the content is 5 and 5. You are a reliable witness. So okay, 5 and 5. Okay, so to be sure, what I call ball is not really a ball. It's something like that I bought by IKEA many years ago. Okay, something like this. Black is not black, you see. It's something. It's dark. White is not even white. Okay. So now let's put inside again. But this one you will not see it. Okay. So this is the one that we can see it. So let's start. So the box is not a box. The ball is not a ball. White is not white, black is not black. Experimental physics. Now let's. Now we are in condition of uncertainty. We are in condition of uncertainty about what? Which one we are picked up? We do not know. Easy to understand we are in absolutely uniform condition. There is no reason. If I make the instruction, it will be black and white. We do not know, but there is no reason why should be black and white. So everybody, if I ask, everybody will tell me 50%. Usually I do this in classes. I think really spend much time. I have to really go fast. I'm already late. So, but what is fun, for example, in this case, these are 5 and 5. Here we do not know. If I ask what is the probability here, black and white, 50%. Okay. If I ask, if I give you a prize to get a white ball, you prefer to choose from here or from there? Now, people, educated people say, oh, it doesn't matter. But there are people which insist and go, oh, this gives me more certainty. Because yeah, I know that it's 5 and 5. Here I don't know. Okay. But what is fun, if I change then the question and say, now I have changed mine, you will get a prize if you get black. What you do now, after that is right, you want to stick on this or change. They stick on this one. Okay. Which is crazy, paradoxically. it has even a name, Ellsberg paradox. Okay, you can find it out. But really, in my seminars, I met many times people insisting on that. And I do seminars also for managers in a decision-making school, students, PhD, and so on, not just the entry levels. Okay. Now, what happens if we extract a ball, look inside, and see the color? So, for a moment, I don't want to mix up everything. For rapidity, I do it myself. So let's see what happens. White, in my definition of ball and white, this is a white ball. Now, what we have learned after this one? We have learned at least that it cannot be all black, because all black cannot produce a white ball. But then, now the question is also, if I make a new extraction, are you more confident to have a black or white? Okay, and usually the tendency is to say white. Okay, and then another question: out of the remaining boxes or bags, are they equally likely, or someone is more likely than the other one? Okay, and now I don't want to answer, but I can tell you with. I have a witness. So I was following a course in Lausanne this winter, spring, and most of the people say, oh, they are equally likely. And then when I ask them the probability, they say, oh, that's very easy, because we have now 25 balls, and the 25 balls, there are 15 against 10, and the probability is 15 over 25, which is 60%, and both answers are wrong. Okay, and why they are wrong? Because when we do the experiment, obviously it was easier to get a white ball where there are more white, okay, and then this one gets more probable. So this essentially can be formalized as a Bayes theorem, but I do by hand with my hands. So initially we are flat condition, okay, but then at the beginning it was more probable to get a white. Always it's more probable to get a white ball if there are more white balls, okay? And then after the first experiment, we get something like this, okay? If I repeat now, okay, I don't do it, but I get white and white and white, everybody understands that after some time we are almost sure that it is be H5. Why? Because we always multiply this times this, and this times this, it's a parabola, and then this times this times this, go on and go on and go on. Every observation provides a little bit of evidence. It's not that after 100 we have just a step in evidence. We multiply everything. So let's go on. So what can we do quantitatively in an objective way? We know the Bayes theorem. I don't have to teach you this one. And what happens after a sequence of extractions? Again, so imagine you have different observation, blah, blah, blah. Okay. Now, the inferential model, this inferential experiment, it is very close to what we do in physics. We try to guess what we do not see without looking inside from our observations. Okay. And in physics, we do not see the mass of the Higgs. We cannot take the Higgs, open it, and read the mass. Okay. Our knowledge is always of this kind. And in fact, the rule of the game, we are not allowed to watch inside the box. We always have to remain with our probabilities. This will be very important from the philosophical point of view. And this is also true in the forensic cases. Those who are called to judge have never experienced by their own senses what really happened. With this, we shouldn't forget. They always judge on reported evidence. Okay, and reported evidence can be fallacious for different reasons. So the judges which tell me, which I hear, I don't talk with judge, in the sense that I want to be certain, I know the truth. They do not know what they are doing, how the word works. I'm sorry, but if you understand a little bit of the word, you will never say you are sure, because it's impossible. Everyone can lie. Everyone can frame you. Okay, and remember, even the sciences are fallacious. Okay, so even if you see, you are not sure, because you also select something on what you see. Okay, now the question is, where is probability? So Now, I don't make very long, but you have understood the story. We all agree that the experimental results change the probability of the box composition, changes the probability of the future outcomes, obviously. But I have reintroduced the ball here. It was exactly as before. There are always 5 balls, but everything changes. If I do next time, we change again our opinion. So where is probability? Certainly not in the box. Otherwise, couldn't change it. Okay. Subjective nature of probability. This is a story everybody suffers. The first time I met this name, subjective, I was, no, it cannot be. Everything is nice, but subjective, I cannot stand it. So, since the knowledge may be different from different persons, or with the same person at different times, okay, they may anticipate the same event with more or less confidence, and thus different numerical probabilities may be attached to the same event. So if somebody enters now and I ask the initial question, the question, he will answer exactly as we did at the beginning, because he has got a different piece of information. This is a guy which is known among physicists, Schrödinger, quantum mechanics. I talk later about the physical probability, because also there are some misinterpretation. So probability depends on the status of information of the subject who evaluates it. Okay. There is nothing bad with subjective. Subjective is not arbitrary. At most, we can reach intersubjectivity if a community which has the same school and the same books and the same data, they will arrive eventually, and they are rational, they are open to change their mind, we can arrive to intersubjectivity. But objectivity does not exist. Okay. Objectivity is only either are the mathematical rules, okay, or it's just the data. 5 in a certain instrument, it is 5. But what means 5? It's a different story. Okay. What we are talking about, I go fast. So essentially, this is the numerical probability set up a quantitative measure of the strength of our conjecture. It's essentially what we say. It's a very complicated sentence, but essentially it is how much we believe something, degree of belief. Okay, and look, we don't have to stick only to events meant as effects. All ideas that our mind can conceive, or to every idea we can attach this quality, this degree. And in fact, I think the first deep analysis of what is going on is done by David Hume, about the roots of the human understanding. Okay, David Hume, and he starts with the concept of ideas. We can have different ideas. They usually we elaborate from external or internal impressions. He also speaks about internal impressions. This is not to be forgotten. And he says nothing is more free than the imagination of man. We can imagine anything. Okay, he had many examples about the Golden Jerusalem. We can imagine anything. It was interested in the Golden Jerusalem. But to some of the ideas we attach a belief, which is a feeling. Okay, so some ideas we just do not believe. We can imagine, but we don't believe it. Okay, and the intensity has a degree. Okay, this is what we call probability. This is what the people always meant by probability. There are things which believe more or less, and then we assign a degree of belief. Something which is just a 0, is just a pure imagination. This is very simple and human, I would say. Okay. Then there is another question: belief versus chance. This is another sophisticated point. Is there chance in the world, or we are simply ignorant? Now there is a confusion between probability and chance. Centuries ago, there was a clear distinction: chance and probability. Probability is our mind, chance in the world. And here about the ignorance and probability, but I was thinking to this expert of the blood, which says, I'm ignorant, so I can say nothing. I think you should change really the job. Because if you ask questions, is this blood trace is more older than 1 day? It has less than 1,000 years, you will reply. And then it's not true that it does nothing. It's difficult really to know nothing. Okay, only if you know some names, you don't even know what they mean, then you know nothing. So if we were ignorant, if we were not ignorant, there would be no probability, but only certainty. But our ignorance cannot be absolute, for there would be no longer any probability at all. Okay. Thus, the problems in probability may be classed according to the greater or less depth of our ignorance. Okay. This is more or less the famous position of Laplace about the intrinsic determinism of the world, but due to our ignorance, we say there are probabilities. Okay. Since time, there is a general consensus that there is an intrinsic randomness in the world, for example, in quantum mechanics, and the people speak about physical probability. You have to be a kind of propensity, a bent to behave in a certain way. And here, for example, David Hume again, that there is no such thing as chance in the world. Our ignorance of the real cause of an event has the same influence on the understanding. Okay? And then we have this concept of probability. And then he makes an example of a die. If you have a die and you have a mark of one type in one or two, it makes two, and four in the other, then you believe more where there are on the mark which is in more phases. Okay. And he makes the example. Go. Let's go fast. Okay. And in fact, the die of which David Hume is talking is very close to, is exactly the box of non-composition of black and white balls. Okay. In this case, the box which has more white ball has more propensity to give white, and then we believe more white if we know the content, but in general we do not know the content. Okay. So the proportion of white balls in a box of non-composition can play the convenient role of physical probability that physicists tend to like. It is an intrinsic property of the box to give white. Okay. As, for example, an intrinsic property of a particle of the Higgs to decay gamma gamma to decays in top top and so on. We consider this as an intrinsic property of the world. But our belief, okay, on the occurrence of white depends on our beliefs on the different compositions, obviously. So if we trust completely, if I knew the composition, then the proportion will be my probability. But if I do not know, I have to take into account all possibilities. How much I believe in the different possibilities. Okay. So only if we are certain about the value of a physical probability, then this value will become our probability, our degree of belief. But usually it's not like that. Otherwise, what we have to do? We have just to sum up the possibility and make a weighted average, and the weight is just the probability of this probability. I know for some of you it's shocking, but in reality, this formula you can note as a probability of a probability, because it is how much probable are these values. And this we usually, in this case, associate to physical probabilities. These are just our beliefs, and this one is a belief. Okay. So again, somebody now will argue, but the physical probability must have a frequentistic interpretation. Not at all. Where is Marisa? Okay, it's not here. There was a seminar 2 weeks ago, last week, about perception audio. Usually we filter with our sense and with our ideas, and some of the people were used to associate probability with frequency. They say, oh yes, probability is frequency, but there is no necessity at all. I've spoken with many theorists and colleagues and so on. So probability and frequencies are somehow related in the probability theory, and we know how. You can predict a frequency from Bernoulli theorem. We can use the past frequency to evaluate probability, use just the Bayes theorem. It is the Laplace succession rule. It's based on probability theory. So there is a connection, but they are different things. Okay. Moreover, so I can agree absolutely that we can associate this physical probability to an object as the mass, the length, and so on. So But for example, in many other physical quantities, physical probability might change with time. Obviously, we have a different complicated model, changes with time. And then, at the most, we can make one or a few observations at different times. How can you make an infinite number of observations? It's absolutely impossible with n which goes to infinite. You're already lucky if you can make one measurement every milliseconds or something like that, if the system is changed. But anyhow, we can model how p changes with time and infer its value with uncertainty to any t. See? So we can make a model which gives us some kind of deterministic explanation of how p changes with time, or even if you like probabilistic, it all depends on the model, but then we have to infer its value in a kind of model with Bayesian reasoning, essentially. So let's go on. Probability versus propensity. Calling different things with different names helps. For example, somebody know here, I don't like the infamous L word, I call it, the likelihood, okay? Introduced by Fisher with the object to avoiding the use of Bayes' theorem. This is, you have to read I.J. Good. Is recognized as a major source of a misunderstanding and of serious errors in physics and elsewhere, okay? Therefore, in my opinion, should be banned or restricted. Sorry, there was banned or restricted. That's within experts, we understand each other, but if you go outside, the people will understand likelihood as probability. Be sure, okay, together with the likelihood ratio, okay. In fact, in a recent talk at Max Cent 2016, I had this talk, probability, propensity, and probability of propensity. Essentially, this one, a bit with less rush, let's say, okay. And this was my idea, although I don't like the word propensity, essentially because also I don't like Popper, okay. There's a strong correlation. Any suggestion I will come for could be a band, but what is important is that we have to keep either different name or just call physical probability, I do not matter, but it's not only in physics, in all our models. When we write a Bayesian network and then we have P and we make inference on P and so on, we are talking of this object, obviously, because it's just, what is a physics quantity? A physics quantity is just a parameter of the model. We have a gravitational theory. Gravitational theory has a few constants, capital G, M1, M2, R, okay? These are just the parameters of the model. You change the model, you will change everything. So important to somehow something which has to, but I would like, because somebody changed, oh, why don't you change probability and change, just call it belief? In fact, there's a lot of confusion on that. Because probability was probability. It was the origin, in the sense that it was understood by Cicero, by Hume, Laplace, Gauss, many others, as is commonly understood. Okay. For the same reason, I prefer Bayes factor, or perhaps even Bayes-Turing factor. Turing was using Bayes factor to encrypt the Enigma code, for example. I think that this name is not bad, especially in UK here, since he has done a very good contribution for a very difficult problem. Sure, I think I end. Okay, so I go on. Bayes theorem, you know, okay. This I don't have to, but this is the way Laplace has presented. Now, cause-effect representation, Bayesian networks, okay. Now we can complicate this Bayesian network. So this is the box composition, these are the observation. We can make some complication. For example, we do not know exactly how the box was prepared, and then we can have reports. We do not see the color. Somebody tell us the color. This, if you allow me, because this is very important, is the clue of everything. Thanks. So let's go on. Okay, so this is the model. I can complicate more in different ways, and no, I go this at the very end. I will use as conclusions. No, I use for historical reasons. I use Eugen. Okay, so I go to the execution. Then I show the monitors. Okay, I enlarge this one. I choose the uniform preparation, which was exactly this one. So if we pick it up one of the boxes, the initial probability it is just uniform, okay, and then this is the probability to observe white and black at any extraction, 50-50, and this is how the reporter, the witness can respond. And in the model, I tell you our model, this one, it's a very simplistic one. The probability to say the truth is 5/6, and the probability of lie is 1/6. Why it is? Because with students I can play with a die, and they just pick up, extract a ball, and then they have to say the truth or lie, tossing a die. So if the die shows 6, for example, they have to lie, otherwise they will say the truth. Now, what happens if we see black? Okay, white, let's say black. Okay, you see black is very easy. B0 goes to 0, and the other one rise linearly. If a second observation, this you see, we will change our probability of the next observation, which is not 60%, it is 73%. Why? Because you have to weigh with more the composition which have more white balls. Now if we do again, okay, and again, but let's restart, because what is interesting now, if we have witness, so it tells white, okay. So if it tells white, we do not believe that it is really white. We believe with 83%, which is 5/5, yeah, 5/6. Okay, and okay, this is our belief. And also, you see, B0 will not go to 0, obviously, because it could have light. We do not know. And then also the next probability will change. Now, and then with this one I finish because I think it's the crucial point. Let's go to the next reporter. Okay. So remember, the first one said white. We believe him with 83% probability. Now the second one also says white. Okay, everything changes. We believe the second one with 90.5%. What is special with the second one? It's better, more reliable. No, the model is the same. Okay, so you can justify in a couple of different ways. So you see, you already had expected the white. Then if it tells you white, you believe more. But what happens to the previous one? Let's go back. In fact, for this is the reason why I was hiding the other cell. Also, the other one becomes more credible. You both trust more. Okay. And in fact, if you had received before this testimony and then the second one, it's absolutely symmetric. Okay. And now it is updated, it's complicated. Now, this is to teach, and I finish here. Sorry for so. Importance of Bayesian networks. Nowadays, thanks to the progresses in mathematics and computing, especially also in mathematics, you have heard this morning the big effort which has been done to make the calculation affordable. It's not just computing. Computing is not enough. So, writing down a belief network is more than half step toward the solution, because then you can ask around, disperse around. Bayesian network have not to be seen only as a technical tool, but also, and more in general, a very powerful conceptual tool. Oh, what is going on? I like, for example, the analogy with a database and entity relation model. Database just are managed by expert people, but any senior manager can understand if this has been well planned, well projected, just studying the entity relation model. You can see if we can navigate and so on. Similarly, if you see a Bayesian network, you can understand if the causal link or the probabilistic link is well done. And you can even do more. You can, for example, many actors of the legal world might help to validate the general structure or the local links, okay? Although the intuition can be misleading in propagation of the probabilities. This was what I wanted to show with the previous example. I've done several times, and you make a little bit more complicated, people get crazy. You don't know. You have only to rely on the mathematics and check that it is done well. Okay. So anyone can add 7 and 7, or even if you say 7 could be 6 and the second 7 would be 6 or 8, but you cannot do the calculation, a long calculation, just by heart. You need a pocket calculator. This was exactly the example that Norma had showed before. So, a similar role should have Bayesian networks in combining pieces of evidence with professional support of experts. Okay, then this for me, it is the end, but, okay, played, I already played, the conclusions, I skipped the conclusion, you understand. There is another one which is important, it said, proper education is, blue means it was blue, needed already in the middle high school level. Because, yeah, now you cannot go to the judges and ask them to make a course on probability. We have to start from the very, very beginning. I think you can do, but it's a lost battle. Surely we have to try. And this is a, sorry, yes. This is a complaint of 3,300 years. This was David Hume, which was reported the complaints of Leibniz. Leibniz will say, so imagine we are exactly 3 centuries ago, Leibniz will say, we do much mathematics, but too little about probabilities, which instead enters every day in our life. Okay, the situation has not changed much. Sorry for being too long. Thank you.
While we set up the next speaker. Oh, we've got technical stuff.
Yeah. Quick question. First of all, as an introduction to the question, what is the Italian word for likelihood?
Probabilità.
Probabilità.
Yes, because verosimiglianza is like, sure, sorry.
Because, say, in German...
In German it's confusing, probability...
Wahrscheinlichkeit.
Yes, I know.
In French it is vraisemblance.
Yeah, all
and in
vraisemblance.
All of which essentially mean the degree to which it seems to be true and can be applied to the hypothesis given the data. And in English there has always been confusion between probability, chance and likelihood as words. And in fact I think it was, although Fisher did not invent the concept of likelihood, that was done before him, for him to emphasize it in that way, I think made a very important distinction between probability or chance as a forward-looking perspective and
likelihood,
as a backward-looking perspective.
But
that was an important concept.
The reason why I'm very upset and very about this, because I see how my colleagues do, and I was doing it, especially because there are what I call unneeded principles, like the maximum likelihood principle. The people make the maximum likelihood, and they believe that the one which maximizes the likelihood, it will be the best, the most probable value. Okay, this cannot hold.
Depends how you interpret it.
In fact, it isn't the depression, but this is, I have seen many mistakes.
Yeah, well, that's misuse of the concept, I think.
Sure. In fact, I saw internally it's okay, but if you go to a court and you say likely, everybody will understand the like. Thanks.
Okay, I think we'll...
So I don't.